Hey guys, so we're wrapping up with Unit 10, and this is our last lesson that we're going to have before we begin our review for our test. Just the purpose of today's lesson is to kind of bring back together this idea of modeling under the umbrella of the now three types of models that we've learned: quadratic modeling, variation modeling, as well as cubic modeling. So we have three different examples, and they're going to encompass those three different models. And they have very different ways that we can create models. So remember that our two main ways to create models is either that we start with a formula. So example one is your formula based modeling. And so we'll take a look at what that means. Um, And we also have a system of equations where if we have four unknowns, which for cubics we have four unknowns, we would create four equations out of 4 points to make a system of equations to solve for your A, B, C, and D. And that's example 3 is your system of equations, EQs for equations, system of equations type of modeling. And then variation kind of is like a formula. Variation is a formula based. So example 2 is also more of a formula based type of model creation. So that's the idea of today is like, how do we create models based off of information? And then how do we find information from those models? So let's go ahead and get started. Here it says find the minimum surface area of a closed cylinder with volume of 500 cubic centimeters. So let's underline a few key words here that are going to tell us what to do. Minimum. If we see the word minimum, that means that we are finding the minimum. In other words, the vertex, right? And we're finding the minimum of the surface area. And so if we're finding the minimum of something, we normally follow that like process of what we've normally been doing. We normally have to graph it on our graphing calculator and then find the minimum there, which means we need to have an equation that represents the surface area. So that is what's going on here, where it says find the minimum of the surface area. Oh, I need an equation, an EQ for surface area. Okay. And then it gives me some information. A closed cylinder is just kind of like an extra piece of information. It's just letting you know that the cylinder isn't open, that it's like a fully encompassed cylinder. And it's because if you were missing the top of the cylinder, then your surface area would change, right? So closed cylinder means that we have a top on this cylinder, and that's why it tells us that. And then it tells us volume. Oh, interesting. It gives us a number for volume. Okay, well, you can write down, well, I know I have an equation for the volume of a cylinder. If you don't remember what that is, it is in your formula packet. I'm also going to go in here and I'm going to draw a picture to just kind of encapsulate all of the things that I know. I know that it's going to have a radius. I know it's going to have a height. And I know that in order to find the volume of a cylinder, it is pi r squared times the height. So I don't remember in your formula packet. I've got it actually pulled up right here. Yeah, it gives it to you exactly like that in your formula packet. So that is ready to go for you. And you have that that's equal to 500. Okay, so all I've done so far is just establish, I've gone through, I've chunked up the sentence even into smaller pieces of like, okay, I need to find the vertex of an equation that I don't have, but I need to make. And I'm given this extra piece of information, which is going to be the key later that helps me unlock the door that is this problem. So all I've done is just first prepare. And now I'm going to try and take a turn into the maze and see what happens. And at the beginning of these types of problems, we don't know where it's going to end, but our main goal is to just start with something. Well, I know I need an equation for a surface area. And with formula-based modeling, we just write out what is the formula for the surface area of a cylinder. Now, that is something I don't believe we have in your formula packet. It gives you the area of the curved surface of the cylinder in your formula packet, which is just this guy, right? That's just the curved surface of the cylinder. And it gives you that it is 2 pi r h. It's because when you open up a cylinder, right? If you've got a cylinder, when you open it up, it's just a rectangle where the height is one side and the base is just the circumference of your circle, right? So that's your circumference of your circle multiplied by the height, which is the curved surface of the cylinder. But we still have two pieces that we haven't included yet, which are your circles, right? The circle up top and the circle down below. So I need to add in two areas of circles. Pi r squared is the area of one. Two of those guys would then cover all of the surfaces of the cylinder. This is not a total formula that's in your formula packet. So this is something that we learned last year in our geometry unit, which we did not get tested on in the final, but we have to know how to find those surface area formulas. So I've done the formula-based modeling step 1, which is start with the formula. Step 2 with finding a formula with formula-based modeling is that I only want one input. And right now I have two inputs. My output is surface area, right? That's what I get. That's my Y value. And my inputs, my X values, I've got two things that are plugged in on this side. I've got an R, which is the radius, and I've also got a height. So my two inputs right now are R and H. And I only want one input when I'm talking about formula-based modeling. So now I have to take a step back and say, well, I've got two inputs. I only want one. So I need to make another equation that I can use to substitute into this equation in order to eliminate one of the other variables. And the only way to eliminate one of the inputs here is to then substitute it out with another relationship. The other relationship that we have to create, and a relationship is just a fancy word for equation, the other equation that we need to create is going to be involving R and H. So then we go back through and say, well, what other information did they give us in this problem that involves R and H? And this is where your key to unlock the problem is right here in front of you, that we were given this information and we haven't used it yet. So how do you know when you're going through a new problem and you're like, how am I supposed to know that that's what I'm supposed to use? Is that you get to the point of a formula-based model and you say, oh, wait, I'm only supposed to have one input and this guy has two. Okay, I need another relationship, more information. And that's when you circle back and you see, do I see visually R and H together with any of the other information that I've created? Or have I missed, if you didn't write this out at the very beginning, did I miss a piece of information at the very beginning that can help me make a relationship that involves R and H? But this guy is going to be key because I'm going to isolate for one of these variables, either R or H, and substitute it in for here in order to make it have only one input. The easiest one to isolate for is H, because I don't want to have to square root when I'm talking about R. So I'm going to just divide both sides by pi r squared. Divide this side by pi r squared. So I get that H is equal to 500 divided by pi r squared. So step 1 with formula-based modeling, start with the formula. Step 2, you need to have only one input. So how you find only one input is you make another equation, step 3. Step 4, isolate for one of the variables and then substitute in. Because H and R, if we're talking about the same cylinder in regards to volume and surface area, they're the same number. So I can take this guy right here and just plug it in for H. So what I get is 2 pi r times, and instead of H, I write 500 over pi r squared. Plus, I just finished the equation, 2 pi r squared. Now, I could leave it like that, and that's totally fine. That is a complete equation. And now notice, how many inputs do I have? Only one, right? I have r here, and I've got r squared here, but that's fine. I can have an x squared and an x in my formula. That's still only one input. So now I've got an equation of only one input. I'm going to simplify this. This pi up here and this pi down here can cancel out because I'm dividing out pi. I can also cancel out one of those r's, and I'm going to multiply 2 to 500, and I get 1,000. 2 times 500 is 1,000. And I canceled out that r, but I still have one r left here in the denominator. So I've still got divided by r plus 2 pi r squared. And now I've just created a formula that shows the surface area with only one input, which is pretty great because now I can graph this. And now we're saying, wait, why did I do this again? What is the purpose? This is where writing down your information at the beginning of the problem, maybe even putting a star next to the like, I need to find the minimum. That is my goal. I got sidetracked because I needed to make an equation and I had to use this information in order to make an equation. But this is the main goal that I need to have. I need to answer for the minimum of this surface area. So I would like for you to go ahead and use your calculator, which you can do, and find the minimum of this equation. When you plug it into your calculator, it looks, oh no, 1,000 divided by x plus 2 pi x squared, right? Even though it says r, we know that our calculator will only accept x as an input. It looks really crazy and my Zoom is insane right now. But it actually looks better with the Zoom that I had for my previous problem, but yours probably looked like this at first if we went to Zoom standard. So then I went to Zoom Fit and it looked like this. And maybe your thoughts were there are no minimums on this, but there actually is a minimum. If you kind of click and drag this guy over, notice it goes back up. And maybe you saw when I first graphed it, it actually does have like this weird parabola side to it where it does have a minimum over here. So if you're like, I don't think it has a minimum, try zooming out a little bit more. And then we can go in and find that minimum. And so the minimum point is 4.349. So 4.3 is our input of r, right? That's the radius. This is the radius that will give us a surface area of 349, which would be the minimum surface area. So the minimum surface area is 349 centimeters squared. Why is this important? Why do we care about this? I know that it seems like it might be a little bit of like a mathy problem where it's like there's no purpose to this, but this is actually one of the more like applicable things that we learn. If you have a company in which you need to package a certain volume of material, you don't want to spend a whole lot of money on the packaging material, right? So maybe you're selling a soda can, right? And you want to be able to fit this specific volume of soda into this can, but you don't want to spend a whole lot of money on the actual materials of the tin that goes around it, of this can, right? So you want to say, okay, how can I make, what are the dimensions that would minimize the surface area as much as possible so I don't have to spend that much on materials? Or maybe you needed to package and sell a material in a box. And so you have a certain volume of the material that you're selling, but you want to make sure that you can fit that volume in the smallest box possible. So keeping that volume of like maybe it's a bunch of shirts or maybe it's dice or whatever you fit into a volume of some kind, then you say, okay, I only want to spend so much on cardboard. What is the smallest box that I can create using this volume? So it's actually a very applicable thing that we could use all the time. Okay, formula-based modeling. Starting with the generic formula, our goal is to only get one input. How we get one input is isolating from another equation and substituting in, and then we have a formula with only one input.